So for the low temperature oscillator, you can write down these branch points where different things can happen. And if you know these branching fractions, you can figure out if the amplifier is going to have gain or not. So the key is that you want, overall, if you stayed inside the cycle, you would get 3 new OHs for each OH you put in. So the amplifier would have chemical gain of 3. But you're going to lose some at these different branch points because something else can happen. You have like side channels where you can lose radicals. And what you need is that the product of 3 times alpha, beta, gamma has to be greater than 1 to get, for this cycle to do anything for you, to make ignition happen. So that's when the gain will be positive. Otherwise, you're getting fewer radicals out than you're putting in, and actually the whole thing will be stable, will not ignite. So this is a critical point, is when I don't know, maybe this is not right. Alpha, beta, yeah. If they were all equal to 1, if there's no loss of radicals, then you can actually do a simple analysis of the cycle and figure out that the time constant would be 1 over the square root of 2 times the K for this reaction times the K for this reaction. Those turn out to be the rate controlling steps, and you can just analyze the Jacobian and figure out that those are the ones that are controlling. And then if you put in the losses, you can do a more complicated analysis to figure out how the time constant of the ignition changes. So this is for the low temperature phase. And this sets the, do you see this is on this log plot, this is a straight line, this is exponential growth. That slope of this line, how many orders of magnitude the radicals go up per unit time, that's lambda. That's this lambda here. All right. Of course, the full system is really complicated because you have all kinds of side reactions, ways you can lose radicals in different ways. And so if you want to do a full analysis, you have to consider those because they affect the alpha, beta, gamma. Some of the fuels show this 2-stage kink, and people record it. More commonly, people don't pay any attention. They might only have a detector that sees the bright emission when the thing really burns. So they only report the final ignition time. They report this whole time from here to here, and they don't do any analysis in between because their detector can't see it. Sometimes their detector sensitive enough that they might see this little kink, and they'll record that also, and they'll call it 2-stage ignition. However, just because they didn't report that they saw the little kink, it doesn't mean the little kink isn't there. It just might be that their sensitivity was not enough with the way they did the measurement to see it. But normally you would expect that this will always be there for any system that starts in low temperature, because when the low temperature process ends, there's some kind of discontinuity in the chemistry. It's like it was doing something, and all of a sudden it's going to do something else. You should see some kinks. And so every time you do a simulation, you always see kinks. And it's easy to figure out what's happening because you can look at the species in the simulation. But experimentally, most people don't have the equipment to be able to see the intermediate species pre-ignition. Their concentrations are really tiny. The knee here, why this goes up exponentially and then bends over, that knee is due to the fact that you've built up enough radicals that radical plus radical reactions start to be significant. So during this region, the number of radicals is so small that radical plus radical is completely negligible. And then the chemistry is perfectly linear, and it's a perfect exponential rise. Just like if you did a first-order differential equation, you always get exponentials as the solution. Once you have radical plus radical, you get second-order terms. The single exponential solution is not true anymore. It's some complicated thing. And practically what that means is this bends over. And typically the one radical reaction that really matters to you is HO2 plus HO2, because you have a lot of HO2s, and they like to recombine, and they make stable, non-reactive things. Come on in, go ahead. All right, the important thing to think about explosions is if there's a positive eigenvalue in any system, it's the only thing that matters. Everything else, all the negative eigenvalues, are just doing little diddly stuff. The positive thing is exponentially blowing stuff up. So it completely dominates over everything else. So if you ever get a positive eigenvalue, that's it. That's the only thing you need to worry about. And in this case, you can calculate the positive eigenvalue, how it depends on the concentrations and stuff, and figure out, you can understand how the HO2, well, you can figure out this number. In stage 1A, when the radical plus radical reactions don't matter, you have a perfect behavior that all the radicals are actually contributing. The HO2s, when you form them, they can't recombine them themselves because those rates are too low because the concentration is too low. So instead, the HO2 attacks the fuel, and it always contributes to chain branching. But when the HO2 concentration gets high enough, HO2 plus HO2 beats HO2 plus fuel. Most of the HO2 is consumed in a useless way. And so then all of a sudden, HO2 is doing nothing for you to make the ignition. So you can see that during stage 1A, at short times, HO2 plus fuel is very important. But then when you get into stage 1B, when the HO2 plus HO2 is important, this is not important anymore because you don't have any HO2s because they've killed themselves off. All right. Yeah, and this shows the dampener. And then you can, if you're good and you spend a lot of time doing algebra, you can derive an algebraic expression for the concentration when the keto hydroperoxide, the peroxide that's forming the radicals in low temperature chemistry, when it reaches its peak. And that's like the end. Once it reaches its peak, it's going down, and it's making fewer and fewer radicals for you. And so something else has got to take over to keep the ignition going. And the peak happens at this point. You take the lambda, calculate with the eigenvalue analysis, and you have to know some temperatures and some delta H's, how much fuel you have to start with, and stuff like that. But it turns out you don't need very many numbers. There's like 10 numbers or something come in, and they give you this tau. And you get this simple formula for the tau, and you can compare it to the experiment. And here I'll just show that the dotted lines are those simple formulas compared to the full model calculations. So these are full models, like 1,000 reactions of the solid lines. The dashed lines is the simple formula that I showed in slide 55 for what the ignition delays would be. And you can see it's pretty darn close. So you can just do a simple analysis and basically tells you what the ignition delay will be. And then if you add the other 990 reactions, you get some fine correction to it, but not much. So basically, physically understand what the source of the ignition delay is at low temperature. So this branch is now understood. The high temperature branch we already understood, and now the only issue is the part in between. Now, one way to look at this is say, well, that's really complicated, and we'll just worry about this branch, and we'll just do an interpolation or something in between. That'd be one way to do it. And in fact, Professor Law wrote some papers with that kind of point of view, and it's actually a pretty practical thing to do. Because you can figure out where these peaks will happen, where the high temperature chemistry will poop out because H plus O2 can't run anymore. And the low temperature chemistry poops out because R plus O2 can't run anymore. And you can figure out those temperatures pretty easily. And then you just know it stops. So it stopped here, stopped here. There must be some kind of smooth interpolation between if you want to know what's going on. Some fuels cannot make QOOH, and they can't do the low temperature chemistry, and particular small alcohols are like this. And then they do the HO2 thing, which we talked about already. And although the HO2 amplifier is less effective, it's interesting that basically what it means, it just shifts things to different temperatures. So propane igniting around 750 K is not that different from methanol igniting around 800 K. But part of this is that propane is mostly working at by the H2O2 cycle also at that high temperature. And so it's really the same chemistry is happening in all these different fuels once you get to the medium temperature region. But the rates are a little bit different because the HO2 plus RH rate is different. And you can do a simple analysis for the medium structure region when you have the H2O2 amplifier. And what you see is you get an exponential rise in HO2, and then you get a quasi-steady state due to HO2 plus HO2. And you can do some simple algebra and derive a simple formula that explains what really happens. So these curves here are the simple formulas, and the dots are actually from doing a full 1,000 species type reaction simulation. All right. So how can we do this now if we want to do a real fuel? There's kind of two approaches. One approach is to go like to RMG, do everything first principles, build a gigantic model, get every number, calculate them all, and if you do it all right, it should work. Okay, so that's kind of one direction. Another direction is to try to figure out, is there some way to lump things and make a reduced model, and then maybe empirically compare it to some experiments and get a few parameters in the lump model, and then just go with a small model. And that would be very helpful for the engine simulators because they really don't want to carry around a 10,000 reaction model when they're trying to do an engine simulation. So both of these guys are fine. So the first principle one, it definitely works, but then you're definitely going to need model reduction. You have to go talk to Professor Liu about how you're going to do the model reduction. And it's quite a project. So it's quite a project to get the full model and make it accurate. And then you have to do a project to try to reduce it and put it into the CFD. And if you do everything and you do it all carefully, it should work out. Okay, so that's the one idea. And that's demonstrated that it can work out if you really work at it. Other idea is that there should be some simpler way because, as I just showed you, like the simple eigenvalue analysis works with you only need 10 reactions. It's way simpler than the 1,000 reactions. So maybe there's some simple way to do this, but I would say this is not demonstrated yet. Now, just because we're looking for a reduced representation does not mean that it's really reduced. The chemistry is really complex. It truly is. If you were able to look in there with a microscope and see what they're doing, there's a zillion different species, all these different peroxides, they're all doing all this crazy stuff. They really are all there, and if you do experiments, you can probe them and see they're there. But maybe we don't need to know about that all in order to know about the ignition delay. So maybe there's a way to represent the ignition delay in a simpler way, because all we care about is really when it's going to ignite. We don't care about if we made this particular peroxy or that particular cyclic thing or that particular, it's not really relevant, right? Because it's all going to burn up anyway once it ignites. So we really just care how long it takes to ignite. So what we really need to do is analyze, is there a way about the structure of the positive eigenvalue, reactions that cause the positive eigenvalue that we can analyze to get a more reduced representation? And the key is you think about, well, we have the QOH cycle, and then we have this H2O2, HO2 cycle, and they're coupled because the RO2 can either react to make QOH or it can react to make HO2. So there's like a choice. And that branch depends on temperature, which way it goes. And then these guys also have branches that depend on temperature. And so we have to, this one depends on concentration because it can react with itself or it can react with a fuel. And then there's actually a set of radicals, R, because a fuel typically has big molecules, a lot of them. And if OH attacks them or HO2 attacks them, it can make a lot of different radicals. Each of those guys have different rates that their peroxies are going to react at. So we have to know those different rates for the whole set. And then if you start with a set of R's, you'll make a set of these guys too. They're all different. And a set of these guys, a set of these guys. So I put braces around to indicate that this is a representation of a whole set of molecules. And that set for a small, simple fuel might be 20 different possibilities. For a real diesel fuel, it might be 10,000 different possibilities. And so that looks really bad to have to worry about 10,000 different possible guys all inside this positive feedback loop. Not too promising. But maybe we can lump stuff together. So the critical thing is to get up to here. So maybe we can just consider that if radicals come in and attack the fuel, they have some flux of stuff that goes out back to this cycle, and they have some flux of stuff that goes out this cycle. And maybe I can just lump all this together as being a property of the fuel. And if I can make a measurement that measures like the fraction of radicals that come out this way compared to how many go out this way, that's like the critical thing I want to know, right? And so I really only need to know a smaller property of the fuel. I don't need to know all the names of all the radicals that are made. I just need to know how many of them make HO2 and how many of them make peroxide. And if I know that ratio, then maybe that's enough. And so this is actually maybe possible. And Ron Hansen's group's been trying to make the measurements of different fuels. You run them into conditions where they're going to ignite. Can I measure like the HO2 that are formed? So I know if I put a certain amount of radicals in, how many HO2s I get out. And then that's like the branch of how much of it goes this way. And then maybe I can also do for OH, measure, he's done that too. And maybe I could even think of a probe for the peroxide and see how much you make. And if I can make those measurements on a fuel, then that might be the number to put on it. Instead of calling it 92 octane fuel, say it's a fuel that makes 22% HO2s and 47% OHs, or whatever it is. And that would be the number to give, because that would tell me a lot more specifically about what I want to know. So that's the idea of this, but this has not been demonstrated to work yet. All right, to summarize. With low temperature chemistry, if you start focusing on the important physics in each stage, you can really start to understand this, whereas otherwise it's very bizarre. You get this gigantic model, it gives you this really strange behavior. It's very confusing. But if you think about it one stage at a time, you can actually understand each stage separately. And you can actually get simple analytical formulas for certain steps, because if you analyze it and say, well, there's only some key processes happening, so I can really focus my attention on what really matters for that particular stage. And overall, ignition is controlled by tens, not hundreds or thousands of rate coefficients. So I only have to really get really good numbers for tens of rate coefficients, which is a lot better than trying to get for thousands of rate coefficients. But still, it's a big project to get tens of rate coefficients that are accurate over ranges of temperatures and pressures. And we haven't done it. So that's a challenge. And sort of how can we optimally combine what we do with theory and what we do with experiment to really be good for practical fuels is like an open question. And I just acknowledge people did this work. And my group and our collaborators have done a lot of this work, but there was very significant work, especially done by Norbert Peters back maybe 10 years ago. Also really important papers to read. And also very recently, Tianfei Liu and Ed Law have also been doing some important papers on sort of the same kind of lines. So. All right. And now the last thing before lunch is soot. All right, so this is a diesel engine, and this is a model developed by John Deck, and this was a very important breakthrough to understand how diesels work. So what you think about is what's really happening. You have the fuel coming out of a fuel injector, and it's a liquid, and it's entraining air. So the momentum of the liquid moving this way is pulling air along this way, which is going to set up a recirculation where the air has to come back like this. Now the air is hot even to begin with because you've compressed it, and it's going to get even hotter once you have a flame here, so it can be very hot. And so you have this very hot air and this cold fuel, and the liquid fuel is getting mixed up with the air because the liquid is not a continuous jet, but it's actually little tiny droplets. So you have a zillion little tiny droplets. You sort of atomize the fuel, and those droplets are flying along at a high velocity because you blast them in there with a high-pressure fuel injector. And they're pulling along the air, and each of those droplets is feeling the air around it, which is pretty hot. And that's evaporating the droplets. And so by the time you get to around here, this fuel droplet area is all surrounded by a region of vapor, evaporated fuel mixed up with the air. The air is there because the air provided the heat to evaporate the fuel. And so it's there, and you've also evaporated fuel. So you have a mixture of fuel and air, and it's at some temperature that's actually lower than the background temperature because you've consumed like the latent heat of vaporization of the fuel to evaporate the droplets. Okay, but it's still pretty hot. And that has an ignition time. So I've made fuel and air at some temperature, and the temperature is above the auto ignition temperature. So after some temperature delay, that fuel and air flows along and suddenly lights, kaboom, because you have fuel and air and there's some delay. Then that makes a premixed, fuel-rich premixed flame along the edge here. Okay, that it ignites, and then depending on the situation, it either can be just igniting and not really being a normal flame. It could just be like spontaneous ignition. Or if the flow is slow enough, the flame that you form from the ignition can actually propagate backwards towards the jet. And then you'll have a real flame front. And I think it can be either way, and it depends on the speeds of the fuel injection. But if you look at it with a camera, you'll see there's liquid, there's fuel air vapor mixing, mixed up unburned stuff, and then you have a flame, and it's burned. Now the flame is rich, so downstream from the flame to the right here, you have a region where you've basically burned up all the oxygen, and you had leftover fuel, so it's pyrolyzing. So the heat from that first ignition, from that first flame, is pyrolyzing the fuel here. So you have fuel, you have CO, you have hydrogen, maybe some CO2, and that's still flowing along because there's still a lot of momentum keeping the flow going this way. And as that goes along, it takes some time. The fuel pyrolyzes, and you make more and more acetylene and more and more and more. And eventually, the acetylene starts to recombine and make benzene, and then they make polycyclic aromatics. And then all of a sudden, it makes a lot of soot. And so you've pyrolyzed the fuel enough for a long enough period of time, you've made soot. So over here, you have a whole lot of soot. And then the soot runs up, the flame kind of runs out of momentum and kind of stops, and you have a diffusion flame where the soot is coming up to the soot and the CO. You have a lot of CO, carbon monoxide from the rich flame. They're coming up against the air, and there's a diffusion flame between that fuel and the air. And so that's what this thing here is. You have diffusion flame all around here. And this diffusion flame actually provides more heat, which can pyrolyze the fuel more, which might be part of the reason why you get so much soot. So that's what it looks like inside a diesel engine. So you have to understand kind of several different things. One thing is all about this ignition time. That's like the cetane number of the diesel fuel. Then there's another about what happens in a premixed rich flame. And exactly how you do the mixture here will affect what happens there. And then you have this pyrolysis zone where you have pyrolysis chemistry happening. And then you have this soot formation, and then you have soot burnout and in a diffusion flame. And all those phenomena are happening at the same time in a diesel engine. And if you wanted to predict, for example, how much soot is going to end up over here, you have to understand all these different things. All right, and here's a quiz, but we don't have much time, so I'm going to tell you the answer. This is a lot of people work really hard on improving diesel fuel injectors to try to make the fuel droplets really tiny and try to make the velocity really high. So why are they doing this? Right? So the reason they're making the droplets really tiny is they want them to evaporate really fast. Right? The sooner they evaporate, the more time there'll be for diffusive mixing of the fuel vapor with the air. So you'll get a more average mixture, and you won't have as many rich spots that are really rich, because those people think they're the ones where you're going to get the most soot from regions that are the richest. Because remember, we did the analysis of fuel rich and fuel lean. If you can keep the number of oxygens per carbon above 1, you don't expect to make much soot at all. So you're trying to get rid of those pockets that are like that, if you can. And then you want the velocity to be high, because you actually want to try to entrain as much of the hot air into this jet as possible to try to evaporate the stuff as fast as possible. And a very crucial thing is you have to make sure the evaporation happens before the liquid hits the wall at the end. Otherwise, you're just pouring diesel fuel into your lubricant, and it's not burning it, which is not what your intention is. So you really need to get a good entrainment of the hot gases to help you with the evaporation. And also, the more entrainment you get, the more you'll also lower the richness, right? You'll get more air in there, so you have a higher air to fuel ratio, which will make you also make less soot. So those are two reasons why you want to do it. All right, observations. If you take a photo, you see a vast amount of soot in there. It is like completely packed with soot. And but the amount of soot you see is vastly bigger than the amount of soot that comes out the tailpipe. So apparently, 99% of the soot that's formed in the engine is actually burned up and doesn't come out. So to me, I've always wondered, why is it not 100%? Why is it 99%? If it was 100%, I wouldn't need a soot trap. I wouldn't have to worry about this problem. I wouldn't have to teach this lecture. So there's a lot of reasons why it'd be better if all this soot would burn up, but it doesn't. And so that's, I think, a really important scientific question about that, about why do some subparticles manage to make it through the diffusion flame. And the current theories are that maybe the turbulence makes some local extinction, and then the soot particles happen to leak through the holes in the flame front where there's caused by local extinction. That's one idea. Another idea is that maybe the soot particles are big, radiate so well that they cool their local surroundings by radiative cooling. And so it's actually so cold that maybe they don't actually burn, or maybe they're just so big that during the transit time through the flame front, the big ones can burn a little bit on the outside, but there's so much fuel in there that the flame can't get them all the way down. So these are all several different theories. I have no idea which one is right. But I think that would be super interesting. I wish somebody would teach me which of those is right. I don't know if it's known. I don't think it's known. Another super interesting observation is if you do an isotope study, you can prove that most of the carbon atoms get separated from each other except in pairs. So if you label two carbons right next to each other on a fuel molecule, then there's a reasonable chance they'll stick together, and you'll see them pairwise at the end. But if you label like 3 carbons apart from each other on a fuel molecule, they're completely separate. You won't see them together at the end. So the isotopes labels show that the molecules basically all break down. It makes sense. You're doing fuel pyrolysis, right? Fuel pyrolysis breaks the molecules down into little bits that are about 2 carbon bits. So that makes sense. The presence of aromatics in the fuel increases the amount of soot that's formed. The hypothesis I've heard people say is that somehow these aromatics catalyze the formation of soot. And then that would suggest that maybe forming benzene rings, the first benzene ring is the critical rate limiting step in forming soot, if this is true. So I've heard people say this a lot with great confidence, but I haven't seen the evidence to convince me that this hypothesis is right. But this is, I would say, the dominant hypothesis, because it's definitely observed. However, it's not observed well enough that it's made it into like our regulations very clearly, and people know what's going on, I would say. Some fuels have a specification, you can't have more than such and such amount of aromatics because they think it might do something about soot. But I don't know where that number came from. And I say the whole thing is a little bit cloudy. And then when you do a flat flame and you put a mass spec above it, you can see that right close to the flame, you don't have any, you have a whole bunch of C2s, and then a little farther up you see some bending rings, and then a little farther up you see 2-ring aromatics, 3-ring aromatics, 4-ring aromatics, and then boom, you see bushels of soot. You never see 5-ring aromatics, you don't see any 6-ring aromatics, and it's like very quick together. You see like, as soon as you see the 2s, you also see the 3s and the 4s, and then boom, you see soot. How that happens, it's like magically all the carbon decides to glom together. And make giant particles of millions of carbon atoms together as a soot particle in a very, very short time, which means a very short distance in the flame, which probably means a very short time. So something is happening that really runs a very fast reaction that combines carbon, whereas before that, the reactions are not running so fast. Again, why this is, I don't think anybody knows, and we'll talk about that in a second. So we'll take a quick look at Professor Hai Wang's slides, which is the lesson 11 slides. So this was a talk that, how do I do this? Does anybody know how to zoom this up to make it show full screen? There we go, view. Control what? Control L. Cool. Obvious, of course. It's got to be Control L. All right, this was a talk that was given at the 33rd Symposium by Professor Hai Wang, who's very famous. At that time, he was at the University of Southern California. Now he's at Stanford. And he said, you know, first thing you got to think about is thermo, of course. So there's two kinds of things that can form particulates. Some kinds of particulates are because the oxide is so stable. So you'll form metal oxides, for example. And it's just because the oxide is very stable and it's a solid, so you just form it. It's sort of enthalpy driven. But soot is actually kind of entropy driven because the enthalpy differences aren't that high between the different hydrocarbons. So it's kind of a little bit peculiar. You want to form soot. And the explanation is because when you form the soot by expelling hydrogen, the hydrogen has a lot of entropy moving around as a separate particle. When your temperature is high enough, that entropy can drive the process, even if it might be endothermic, to knock the hydrogens off. So here's a picture of this, is that for sure to form acetylene, it's endothermic. And you get some exothermic reactions like acetylene to benzene, but these other guys, they might be slightly uphill even, not so clear. But when you put the entropy in, the fact that you're making more and more hydrogen tends to make the reaction run. The delta G is favorable because you're making more and more particles. But this is only true if the temperature is high enough. So that's the idea. Of course, it's obvious. You make bushels of it, right? You guys have probably made soot yourself in the past. It's not hard. The ancient cavemen knew how to make it. People used to make tattoos out of it, art. People have been studying soot for a long time. Soot is, at the inside level, you have kind of two types of soot. You have soot that's kind of layers of aromatic sheets, and it looks like kind of like onion structures. You see like it has layers? And then you also sometimes get soot that's kind of amorphous, where it doesn't seem to have any pattern. And you have both of those things being formed. And if you cook soot longer, it gets more and more to be the aromatic thing. So that's probably the more stable one. You get rid of more hydrogen. And then these particles get to be a certain size, and then they tend to stick to each other, and they make these kind of fractal agglomerates. And the details about how this happens is super important technologically, because this is how like ink is made. Ink is soot particles a certain way. If you make them a different way, they're good for the material to put in tires, to make tires strong. And it all depends on details of exactly the pattern of this fractal pattern and exactly what's on the coating on the soot. The top surface of the soot, does it chemically bond well to the tire material? That's really important for the material properties. For the ink, it's like, does it disperse well into the solvent so you can get the ink to flow? So there's companies like Cabot that's like their whole life is all worrying about exactly the different properties of the soot you make, and exactly if you burn it a different way from a different starting material, you make slightly different things, which actually technologically are very different. And you can buy like 10,000 different grades of carbon like this, all made different ways, all with different special purposes. And there's like customers who buy them and stuff. And there's a whole journal called Carbon. It's all about this topic, just about structures of carbon. It's pretty amazing, actually. And you can do a lot of things with it. So these are all different things people use. You can actually use soot to make buckyballs, to make nanotubes. You can make graphite. You can make all kinds of stuff. Carbon black is the biggest by mass. Maybe by money is probably like the ink. If you guys ever bought that ink, you know how expensive it is. And they've been using it to make solar cells. It's very important for heat transfer in furnaces. The soot radiates, and that's the way most of the heat is transferred to the furnace boilers and a lot of furnace designs. And of course, as we talked about, it's a really major air pollutant with very significant health effects. Also, even climate effects too. So the dirty soot changes the heat absorption. Albedo, like the white soot can cause clouds which can reflect the climate. So you have like positive and negative effects on the heat balance. A very complicated topic. All right. So people have been trying to figure this out for the longest time. And recently there's been a lot of interest in trying to make engine designs and combustor designs that would make less soot or burn the soot out. So people will worry about like doing CFD with soot models to try to figure out how to do it. And these are references. You have them in your notes, a lot of different references for it. So this is the chemistry part. I'm just going to talk about the chemistry issues. So the idea is that you somehow get up to a point of making a single ring aromatic, and then somehow this can combine and make moldy rings. Now, one theory people write is that it goes on to do this, but I would say that there's no experimental evidence that these guys are present free in the soot. So somehow you get up to these kind of sizes, and then something happens magically, and you make something complicated. And then eventually these things kind of get big enough that they can just coalesce, that the van der Waals attractions are high enough to overcome the thermal energy wants to separate them. The van der Waals attraction wants to bring them together. You have to be pretty big to have a big van der Waals correction. So when they get big enough, at some point they'll start to coalesce. Then as the flame cools down, so right in the flame front, it's super hot, but then you usually have like radiative cooling and other kinds of cooling. The thing cools down. At some point you might start having coalescence more of other stuff that's in the flame was trying to absorb into the soot particle. Actually, soot is very used as activated carbon as an absorbent. It's a really great absorbent for absorbing all kinds of stuff. It's used to like air filters and all kinds of things. And the same will happen in the flame, that the soot you make can actually be the absorbent and absorb leftover hydrocarbons that haven't burned. Any stuff you got there probably will absorb it when the temperature gets low enough. And when you measure soot coming out, say, of an engine, about half the mass of the soot is like solid stuff, and half of it is stuff that if you wash it with a solvent, you can wash it out. So it's like liquid stuff that's absorbed into the soot. So that's called a soluble organic fraction. Again, I don't think anybody ever explained to me exactly how that happens, but it's definitely observed. All right, so there's kind of idea, there's different issues. So there's gas phase chemistry is going to make your first couple rings. Then there's pH chemistry. Somehow these polycyclic aromatics stick to each other and do something. Then somehow that all makes something we call a nucleus of soot. And after that process, somehow it becomes irreversible. Once you make like a nucleus of a soot, it doesn't come back. And you just keep making bigger and bigger soots. The soot grows, and then eventually they grow to a certain size, and they stop growing, and they stick to each other. And this last part about the growth and sticking together, there's a professor named Marcus Kraft in Cambridge University. He's like the world's expert on this, and he has really good models for all of it. Once you have the soot, how it sticks together and moves around, and what shapes you'll get, and all that kind of stuff. So that's sort of pretty well understood. So here's one example. This is one from Balthasar was one of the students of Marcus Kraft, and Frank Locke worked together, and they could see, why when you observe it, you always see little balls, perfect little spherical balls. And how the heck do the atoms know they're supposed to arrange themselves in little tiny balls? The balls are always about the same size, always like 30 nanometers diameter. Any soot, it's always made up of these little balls. So these guys did a simulation and figured out sort of why it sort of what wants to grow that way. It tends to grow where there's like the highest curvature the most, and that tends to smooth out the curvature and makes it eventually go round. So this paper explains that. People invented this really nice thing called a scanning mobility sizer, where you can see the size of the soot particles from pretty small sizes. Here's like, this says 2 nanometers, but maybe, yeah, 2 nanometers out to like 30 nanometers. And you can see that like initially you have a whole lot of small stuff, and eventually you start growing some bigger stuff, and you get this like double humped size distribution that you have a whole bunch of small stuff, and then you start to make a hump of bigger stuff. And the hump moves, the peak position moves as the big stuff tends to grow into its like final size. And with that instrument, this is a very good way, again, it's one of these things where you can test a model very well because you have a lot of data. But if your model doesn't match this, it doesn't tell you what to change in your model to make it work. So here's another map of the size distribution. See, this is like I don't know what the difference is. Here's the experiment. This is the experimental data. And then these are models about what should happen. And you can see it doesn't quite match. It's kind of like it, though, right? So the models are sort of on the same ballpark to understand what's happening. Now, chemically, it's a total mess. This is mass spectrometry of nascent soot as it's like starting to form. And you see you have a peak at every single mass. The mass spectrum has every single freaking mass in the whole of all masses. As far as your mass spectrum will go, there's something there. So every molecule you can imagine is actually there, and they can see them all. Each of these peaks is like a molecule, right? There's like a lot of molecules there. It's like analyzing grass by looking at your lawn, you know? So this is quite confusing. And how the heck you can do chemical reactions that would make all this different stuff, I have no idea. And I don't think anybody does. So this is like a huge challenge. We have the data. We have the data about the sizes. We have the data about the molecules. And we don't really have models that really understand this. But you can try to make your experiments better to help the model. So one innovation by Professor Wang was to run a flame up against a wall with a little pinhole in it. And it turns out that you can, this really simplifies the CFD analysis. So you can really analyze what the flame should be doing. And if you do the pinhole correctly, you can sample what you get. And so you have very good boundary conditions for doing a 1D. You can convert this into like a 1D simulation because of the symmetry of the situation. And then you can, if you had a chemistry model that was correct and a model that was correct, you'd be able to solve it. So at least as that part's done. And then you have data that you could compare with. All right, so we have a lot of problems. We don't really know the pH chemistry that well. We don't know why the particles incept. What's the nucleation? What is that? And we actually know that the answer to this is no. The nascent soot is not the same as the mature soot. So there's a lot of chemistries happening inside the soot particles after they already form. It's changing the actual number of atoms inside there, and the carbon to hydrogen ratio is changing. The hydrogens are getting out of there somehow. And then there's a mechanism that was proposed a long time ago called the Haka mechanism, that people thought was the main way this formed. I would say right now it's doubtful. People don't know how important that mechanism is. So here's something about the pH chemistry. This is the Haka mechanism where you make radicals, you add acetylene, you make another radical, you add another acetylene. Sometimes these things fold up, and you keep on adding more acetylenes and more acetylenes, more acetylenes. So this is like a mechanism where you keep on adding pieces that are C2 over and over and over again to form your soot. And you can do it. You can make a model like this, and definitely these reactions happen. There's some question about how far it goes. However, if you do a sensitivity analysis with that model, you see you're sensitive to a ton of things. So the yield of pyrene, say it's a 4ring aromatic, depends on all these different reactions with about the same sensitivity to all of them. So this is a problem because it means you have to have a lot of numbers all accurate. You can't just focus on one or two things. You have to really understand a lot of things. And this is just to the rates. If you do the thermochemistry, it's similar. You're sensitive to a lot of thermochemistry as well. By contrast, if you're doing a flame speed, you get a lot more common like this. You have like 1 or 2 reactions that matter, and all the rest of them are like diddly little things that hardly matter. So that's a lot simpler. You can just focus your attention on a couple of reactions. But in the soot case, you have to look at a lot of reactions because they're all about equally important. So this is a big problem, practically, because it may require a precision in the chemistry that's just unavailable. You need lots and lots of numbers to be really good. You can't just focus attention on a couple. And and the precision you need is pretty high because you're pretty sensitive to a lot of numbers. So this is really a problem. And in addition, this is just with one model, but in fact, it's currently believed that actually there's a whole lot of other reaction pathways that this model missed. So there might be a lot of other reactions we're sensitive to as well, in addition to all these ones. So that's very unfortunate. And sort of what's going on is that the thermo is pretty balanced. This is only 1 kcal per mole scale. So the thermo is like bouncing along plus or minus 1 or 2 kcals through all these steps, many, many, many steps. You have to get up to like, 1 million carbons eventually have to be bonded together to make the soot particle. So this is only going out to like 10 or 20. And so you can see this has got to go a long way. And if we're off by 1 kcal per mole somewhere here, we might get a barrier that's going to stop the whole thing from happening or whatever. All right, and then there's other pathways are known. This is the C3 propargyl radical recombination. Is it? Yeah. So it rearranges and does stuff. And then all these other pathways have also been found that also make polycyclic aromatics. So there's a lot of ways you can get there. And now they've done the mass spec. It shows some of them there. They've done it now with the synchrotron, and they confirmed, yes, there's masses, there's molecules formed with every single mass for over hundreds and hundreds of mass range. And comparable intensities, too. All right, now let's talk about soot nucleation. So somehow you have to get from molecules to particles. What does that mean? So this is our definition of species thing. And the problem is you don't see the nuclei. You see indirectly their effect because if you have a lot of nuclei, you'll make a lot of particles. If you have a small number of nuclei, you'll make a small number of particles. When the particles grow big, it's easy to see them and you can count them. So we know how many particles we made. So we know how many nuclei we must have formed, but we don't know what they are. They must have carbon in them. That's probably not the only safe thing we can say. And then the chemistry is going to change. The C to H ratios change depending on the mechanism. And then actually it changes with time as time goes on, from about 1 carbon per hydrogen up to about 10 carbons per hydrogen. So we must do a lot of reactions to kick out hydrogen. You get this kind of bimodality, which implies that the nucleation kinetics are second order in something. So there's something plus something must come together at the rate limiting step to make the nuclei. But we don't know what the two things are that we recombine. But definitely this bimodal. And then here's the mass spectrum. You can see some periodicity. I would say that the more recent synchrotron experiments don't show it so strongly, so you actually see peaks in here too. But you do see some kind of lumps, which suggests that maybe it's when they're big enough, somehow you get pieces of things coming together. But these are pretty heavy. So this is like 600 mass units difference, right? Yeah, 600 mass units, maybe 500 mass units. So 500 mass units, how many carbons is that? That's like 30, so chunks that are like 30 carbons at a piece are coming together. So that means we need to have models that go up to, all the way up to things that are 30 carbon pieces that are molecules, and then maybe somehow they glom onto each other. But currently with RMG, we get above 10 carbons, we're getting in big trouble. So it's just quite a stretch to get to 30. All right. I think, and people thought, well, maybe just like the molecules would stick together, these big PAHs, but then if you actually calculate their binding energy of two of these molecules, it's too low. And you can see it from the vaporization. You can vaporize these molecules at much lower temperatures than the flame temperature, so this can't be the explanation. They won't bond. So in this talk, Professor Wang proposed a new idea that maybe there's like persistent radicals, that the soot particle is actually a radical, the whole soot particle. And then that way it can be a chemical addition reaction of a radical to a multiple bond. And those reactions are known to be really fast, so low barriers. So maybe that's the explanation. But then you have to understand what's the electronic structure that would allow some big molecule to consistently be a radical and not go away. But there's a cool observation that if you take a piece of coal out of the earth and you put it inside a magnet and you run microwaves at it, it shows you the signal of unpaired electrons, electron spin resonance. So in coal, it's been sitting there a million years. It still has a radical there. So there's obviously some structures that give you very persistent radicals that don't want to go away. But what they are, we don't know. So this paper is like one proposal of some possible one. I would say not convincing. But somehow there are some electronic structures which much do it. So if this is true, if say their stable radicals play a role, then we'd have to understand what they are. We'd have to figure out their binding energies. We'd have to figure out their rates. And then we'd have to be able to probe them. And then we can make a mechanism. So basically, if my hypothesis is right, I have to do 27 other steps. And then maybe I can have a model. So that's the status of it as of today. And so you can try to make models for this. And then this other confusion is that baby soot is completely unlike mature soot. Everything about it, the structure's different, the spectrum's different, everything's different. So soot is not soot. Soot is like, there's like 47 different types of soot, and they are all changing into each other by unknown reactions currently. So everything's very simple. So people have tried, I mean, try to explain. Numerous hypotheses have been proposed with some weak evidence in their favor that I would say is completely unclear. So it's wide open. So any of you guys who wants to be a professor, if you have the great idea of how to figure out the soot mechanism, you'll have no challenger. You're there. All right. And it was interesting. This was a paper, a book published about making soot, and it shows Sisyphus pushing a soot particle up the hill, trying like, how the heck can we get soot? Whatever we do in our models, we never make it. But he says, really, we make it, right? You do anything and you make soot. It's like not hard at all. So it must really be energetically downhill, and there must really be a low barrier pathway that makes it. It's just because we haven't found it yet. Doesn't mean it doesn't exist. So that's the challenge there. So he thinks we should take the book upside down. And then if you could figure out soot, you could work on these other particle problems, which are very similar. It's like we don't know what the fundamental nuclei is. We know we make the particles in the flame. That's how they're manufactured. Like fumed silica, titania is used for opacifiers. They're both made in flames. It's easy to make them experimentally, but again, we don't know what the mechanism is. Somehow it goes from chemistry, little molecules, and then boom, we have particles. And we don't know what the nuclei are. We don't know what's the critical thing. We basically don't know anything about it. We just know, we know the first 3 steps, and then we know the final, we have bushels of powder coming out. And that's about what we know. And we have a lot of analysis of the powder. We can tell you everything about the powder. And we tell you everything about the starting material, stuff we're feeding it. And that's about as far as we know. So it's like magic happens and it appears. But these are very technologically important, and people spend a lot of time messing around to try to make this stuff better or whatever qualities you want. But it's very highly empirical because people don't really understand. And the same with soot. All right, we've got a few minutes left. Let me just go back to the final day lectures. All right. So this is philosophy. So the last quiz of the course, we have models, empirical models, that actually predict the amount of soot pretty well. And maybe some of you have used them if you try to do engine simulations. However, if you look inside these models, every single one of them has an irreversible reaction. And if in the solver you make that equation reversible, then it makes no soot. So the models are based on a lie. Right? There's a lie is that I picked one reaction in here, and I just made it irreversible, and then I get an irreversible production of soot. And that's the story. But so the models all violate the second law of thermodynamics. But, you have an engine, you need to run a simulation to get some soot. They make some soot. And it's like within an order of magnitude of what you see experimentally. So the question is it okay to disseminate and rely on models which are actually completely incorrect? So this is maybe, I don't know if this is ethics, philosophy. I'm not sure what's the question here. But talk to your partner about this, because you're going to face this problem immediately if you work in this field. All right, do we have any positions about this? What's the answer? What do you think?
So, if you know it works, and you have to really spell it out that it's fundamentally incorrect, but it works. So as long as you do that, then you've served the purpose of something that they can predict something with, but they got to be careful not to.
Okay. I mean, I guess if you look at it from that point of view, you put your stamp on the top. You say, I, Joe Blow, do hereby promise that this model worked for condition X, but I know it's completely wrong. Use at your own risk. So you put the warranty on there, the legal language. I guess it's not so different from our regular models, right? We give any kinetic model, we've left out something, and we still, we give it to people and they're not mad at us. But at least we don't have, in the part we wrote down, we don't have a clear lie, whereas in these models, it's clearly a lie right from the beginning. Any other opinions about this? Yep.
I think our models are wrong, but some of them are useful.
Okay. So therefore, I don't have to warn anybody they should know, because of course all models are wrong?
I mean, as long as it gives you some reasonable result and it's useful for you.
I see. So this is like so should I forget the disseminate part? So I can rely on myself, because I know it's false, and it's okay. But I'm not going to foist this off on my poor children. And then they might feed them lies. It's like telling about the Easter Bunny or something. Is that? Yeah?
Actually, a good way to compare your method, it works right or wrong, compare it with the previous models. And if you trust that, if you believe that your model is working right logically, you see that your results deviate in some percentage with the previous model. And you can maybe underestimate some of your errors. Under some levels of errors, maybe you can use them.
Okay, so you're saying that if my model that's a lie is better than the literature model, which is also a lie, then I'm entitled to disseminate my model. Is that? Yeah?
In my opinion, if a model is incorrect, doesn't mean it doesn't have some truth in it.
Yeah?
And also you can, based on the previous model, they have some truth, and you can grow your understanding little by little, and you can make use of it.
Okay. Yeah?
2 points. The first is, for example, I'm doing ice engine, and the soot formation ice engine is sometimes very serious. So, but if we do soot prediction with the soot model coupled with the safety code, but we do not qualitatively compare with the dispersion data, but we compare with the trend. If the trend captured, we can go into the safety calculation result. We see where the soot is produced. So maybe this result can help us to better design our engine.
Okay, so you're saying that the model, even though it's not really true, is close enough to true that I'll use it.
Yeah, but as you say, it is irreversible. There is no irreversible.
Reversible, yeah.
Yeah. But we know how it produced. The model predict the part right.
Okay.
Part of the prediction is right. And the second is we are the frontier, but our past. So there are young scientists. They will look forward to what we do, and they will know our fault. So they will do better.
Okay, well, so that's my message to you guys. You're the young scientist. Personally, I think these models are terrible. If one of you could please come up with a model that had reversible reactions that actually made soot and actually looked something like experiment, I would be so grateful. So I'm hoping that one of you guys will do it. Yeah?
So I wanted to say, I personally wouldn't call it really a lie, because in science and engineering, we make assumptions all the time to get things done. So a lot of our models, we assume an incompressible fluid or assume ideal conditions. The whole ideal gas law is kind of a lie.
Okay, so it's true, right? All of our models are not true. So the fact that we just happen to break the second law of thermodynamics is no worse than breaking the, right? Is that what you're saying? Okay. Yeah, what is your opinion?
I think all engineering is a compromise between cost and what you repeatedly call the truth.
Okay.
In my career, I've run multiple $1 million projects, and there comes a in my life, where management on numerous occasions instead said, we want an answer now. It does not have to be true, but you have to sign it.
Yeah. Did you guys hear this? This is a very important statement. So you're doing a big project that's going to be expensive, and for sure there'll be a deadline. And it's someday the deadline comes, and a manager comes, and they say, okay, you're the engineer. Your job is to write the answer, the thing we're going to implement. And in addition to that, in America, as the engineer, you sign off on it, right? So if things go wrong, they're going to blame you. And the manager says, sorry, today's the day you got to do it. We know you haven't found the truth yet, but you got to give us something, because tomorrow we're going to start building it or whatever. And that's the truth, right? And that's the engineers are always in this thing, is you have a deadline and cost pressure, and you want to be as close to the truth as you can, given those constraints, which can be pretty strong constraints. Yeah.
That is the truth, but there have been several occasions where I refused to comply.
Okay, so this is right. So this is actually maybe the power the engineers have, right? The boss tells you to do this, but you're the one who has to sign it. And if you don't sign it, they're not going to do it. So that's where your judgment call comes in. Yep.
I think we have to distinguish between the approximation and violating the physical law. Some of these are approximations, are not a violation. For example, for CFD, if I violate conservation, all the answers are wrong. But if having something better than having nothing, you can go ahead and use design something based on it. It's not going to even take off.
Okay, so that's right. So I think that's why I get so agitated about this one. Is like, I'm used to having imprecise numbers and making numerical approximations. Somehow, the second law of thermodynamics seems more fundamental to me, so it makes me feel very upset to violate it. All right, enough on this. Summary. Fuels are a major advantage, a major boon to society, and also a major bane to society. The very, very positive effects on human development, on our whole society basically is based on the use of fuels. And also, they cause a lot of problems. And because of this, something's going to change. And you guys will be, you're the generation that's going to do the change. And we have really excellent understanding of the small molecule combustion chemistry and of fuel pyrolysis, at least up to the point when soot starts to be formed. And we're just beginning to understand low temperature ignition, NOx chemistry, and the formation of the PAHs. And to me, I think there's some kind of conceptual problem in this soot formation. I don't know what it is. And there's new tools like the accurate rate calculations, automated mechanism generation, and actually other things like new experimental tools as well that are making it possible to push forward, but they all have problems, and nothing is like completely solved. So more work is needed, and you guys are prepared now to do it. So good luck.